we move on. So I get to draw it, three-dimensional. I have to know what these things look like. So it's enclosed by this cylinder. I gave you the hint that it's a cylinder, but you should recognize that as a quadratic surface. It's a cylinder, radius 3, opens out the x-axis, right? So it looks like this. Radius 3, it's going out the x-axis. So my x-axis goes through here, and of course it extends in that direction forever. But I know that's in here. And then I have x is 0, which is the back wall, right? I'm only in the first octant, so I'm only going to draw this back wall. So the back wall, I have, let me do z equals 0 because it's easier. Z is 0 is the ground, right? Then I have a plane, this right here, this plane, y equals 3x. So this plane, if I look at it on the ground, it's basically the line y equals 3x, which would look like this. It goes through 0. If I plug in 1 for x, what does it spit out for y? 3. Here's 3. So if I go out 1x, I'm going to be here at 3. I don't know, something like that. So I know that that cuts through like that, right? And that line goes forever. And there's a sheet of paper that comes through and cuts through, just like that. Then I have my cylinder. Now my cylinder goes in both directions, but the back wall cuts it off, doesn't it? So if I'm looking at the back wall, it's this quarter circle, isn't it? And as it moves down through here, this plane cuts through it, doesn't it? This plane slices through the cylinder. So if I attach from here to here with the curve, I can see kind of a slice of this thing. Do y'all see how that plane cuts that cylinder? And if I connect these together, it's like a slice of bundt cake. Have you ever had a bundt cake? Kind of like a slice of bundt cake. Not quite, but close enough. Right? That's our region E. I draw its shadow or projection onto the ground. I draw that in two-dimensional space over here. X, Y, it goes through 0. It hits up here at 3. And then over 1, up 3, hits this point. So this right here is that piece on the ground, right? That on the ground looks like a type 1 region to me. I like that as a type 1 because if I draw a vertical segment in there, the top and bottom are always the same curves. My x's are bound between two constants, so I should be able to set up my restrictions on x and y right now. X restrictions are 0 to 1. Y restrictions, so you have to know the equation of this line, which is y is 3x. And then the equation of this line, which is y is 3. It's constant. So this is going to go from 3x to 3. And the last thing now is my restrictions on z. So the bottom of this solid is 0, isn't it? And the top is this part of the cylinder, isn't it? So the cylinder equation is here. You have to take that and do what? Solve for z. You're going to get a plus or minus square root when you do that, but you're only looking at the plus because it's the top. So solve that, you get z is equal to square root 9 minus y squared, right? So this is square root 9 minus y squared. Bless you. And then you set it all up, right? So you'll have triple integral 0, 1, 3x, 3, 0, let's see, square root 9 minus y squared. We are integrating z, d, z, d, y, dx, because it's type 1. And then you go do it. All right. I was just thinking about this. Are there quadruple integrals? No? Sure. Not in this class, but I mean, could there be? Yeah. And if you did it, you could say, okay, well, imagine that we have this, our region, I'll call it, I don't know, E, F, okay? It's a quadruple integral over F of some function of not 3 variables, but 4 variables. I'll say t. D d, yeah, I mean, like dv was d volume because the E had a volume, right? But what is 1 dimension higher than volume? You know what I'm saying? Like we don't have a nice thing for it. So I could call pretty much anything I want. dh, because we could call it a hypersolid. Sometimes a solid that's one dimension higher than 3 is called a hypersolid. I could do that. And what you would have to come up with is restrictions on x, y, z, and t, right? X would be between 2 constants, let's say a and b. Y would be between 2 functions of x. Z would be between 2 functions of x and y. And t would be between 2 functions of x, y, z, x, y, z. So you can generalize this. But we start to lose application because we really only need 3D, 4 really, to work with a lot of things in the real world, 3 or 4 dimensions. So, all right. This is what I was saying. There's different types of triple integrals on, casting shadows on different planes. Now we move on. So if you recall that from double integrals, if you're taking the double integral over d of 1 dA, that this represented the area of d. Remember I said that? If you take a double integral of the constant 1 function over some region d, this answer is the area of the d. Well, it works exactly the same with triple integrals. If you take the triple integral over e of the constant 1 function dv, you get the volume of e. Didn't we just do that problem? Oh, no, we didn't. Sorry, we did not do that problem. That problem is the exact same region, right? That's the exact same E that we just had. But there's not a function that we're integrating, right? It's saying find the volume of that, right? Find the volume. So all I'm going to do is set up the same triple, 0 to 1, 3x to 3, 0 to square root 9 minus y squared of 1. dz, dy, dx. If you integrate that, then you will get the volume of that solid. See the difference? Okay. It turned out to be 3. I just had the computer do it. Now, I think that's where the notes end, right? Is that where they end? I spent some more time today. There's a little more in this section, I have not updated these notes online, but there's some stuff at the end of this section I think is worth looking at. And we won't do an example, but we'll talk about it, all right? That doesn't mean you won't have it for homework. You will have it for homework, but I'm not going to work through one. Application of a triple integral. We saw when we had a lamina last class, if that lamina had a density function, we could find its center of mass. We could find its moments of inertia, things like that. Well, we don't like laminas because we live in three-dimensional space. So, I mean, I'd be more interested in finding the center of mass of some object, right? This is three-dimensional. So if I have an object in three-dimensional space, and I know its density function, then we have the following results. The mass is the triple integral of the density function. Wasn't that exactly what it was with the lamina? The mass was the double integral of the density function. So the mass of a three-dimensional object is the triple integral of the density function. Then we had, with last class, moment functions. But because we were only working with two variables, we had the moment about x, the moment about y. Here, because we have three variables, we have what's called the moment about the xz plane, or sorry, the yz plane. Here's what it is. The moment about the xz plane, here's what it is. And the moment about the xy plane, which is this. So the moment about the yz plane is the same as the mass, with the exception that you have to multiply by x. Moment about the yz plane is the same as the mass, except multiplied by y. Moment about the xy plane is the same thing, except z. Once you compute all of these, then you can find the center of mass. The center of mass is an ordered triple. It's your x, y, and z coordinates. The x coordinate is your moment about the yz plane over the mass. The y coordinate is the moment about the xz plane over the mass. The z coordinate is the moment about the xy plane over the mass. So there's a lot of integration that has to take place for you to find it, right? But it can be done. Then you have the moments of inertia, which is the object's resistance to motion, to being rotated about something. So if you want to know the moment of inertia about the x-axis, so you have this object, you're trying to rotate it around the x-axis, its resistance to that motion is going to be measured by this triple integral. So do you see that density function again? But you multiply by y squared plus x squared. And then the moment about the y-axis is this, and the moment about the z-axis is this. So you might imagine those could get pretty messy, but they're doable. I have the homework assignment. Yay. I haven't done these on video yet. I plan on doing those, starting those tomorrow. What's your question? What?
It's like on the take-home, where we have to find the moments of inertia, on the last one, you said which one is easiest, about the x-axis or about the y? So how do we know? Is it like is it the shortest moment of inertia, or you gotta stop recording?
Someone asked me that question last time.
Did they?
Yeah, right?
And
I said,
Think of it.
Look it up.
I remember that.
Be resourceful. I'm sure you can find it out.
No, I just remember
Yeah.
that example.
What you could also do if you wanted to try and, I don't know, see what you can do.
No, I got you.
Okay. All right, that's the homework for that section. Got it? We got 20 minutes left. We have enough time to get into the next section. 12:06. Let me save this. So that's it for 12:06. Just do those problems. All right? Triple integrals in cylindrical coordinates. So just like we did with double integrals, we had type 1, type 2 regions. Then we realized, hey, there's some regions that are not very good, you know, as far as they don't look like type 1 or type 2. So we came up with polar coordinates. So now we have this thing with triple integrals called cylindrical coordinates. And here's how it works. It'll look familiar. Actually, it's going to look very familiar. This is just a three-dimensional version of polar coordinates. We use the same exact conversion. X is r cosine theta, y is r sine theta.